Ready. Wait, just a moment. Are we set up? Okay. So, hello everyone. This is the moment you've all been waiting for. Hello. Um, Good evening, everyone. You're here because presumably you wanted to know the answer to this question. What is new in AI and ML? I'm Willie, the Director of Technology for the Artificial Intelligence Society at UT Dallas, and I'm here to help answer that question. So, first of all, you've likely heard these terms before, AI and ML, artificial intelligence and machine learning. But I have a hunch that most of us here aren't on the same page when it actually comes to knowing what those terms mean. They become very loaded and have very different meanings depending on who you ask. So, first, we're going to go on a bit of a journey through the trees that make up the forest of that field, so to speak. We're going to understand really what is AI and ML before we talk about what is happening now in the field. Uh, so, first of all, this isn't going to be very technical. It's going to be more of an overview because this is more of an introduction. This is like an on-ramp to AI and ML. So let's think about our approach here as we answer the question, what is new in the field? I could make this could have been a quick video, top 10 new things in AI and ML. But let's take a more curious approach here. Let's ask questions and find out why are the most recent advances in AI, like Google's AlphaGo agent that can play Go better than humans, or OpenAI's GPT-3 model. Why are those so notable in the first place? We are going to find out. So for the live audience that is here, if you have any questions, just leave them in the chat and I'll try to address them as soon as I can, or one of our other officers in AIS will try helping to answer. So let's proceed. So I'm going to ask this question. What is artificial intelligence? Does anyone in chat want to attempt answering that very big question? AI is a very, very big thing now, as I'm sure all of you are aware. So we'll move forward. Here's what AI is to some people. For some reason, well, Hollywood and much of the media that exists online, people tend to portray AI as this, or this is what they tend to have in mind. They have, uh, I mean, in a way, it kind of makes sense. AI in many ways poses a unique opportunity and a unique challenge for humanity, which is why it has caused a lot of fear and uncertainty doubt, but it has caused a lot of fear in the populace because humans, for the longest time, have been known to be the dominant species on Earth. We were uh, not just the most clever, but we were also the smartest, right? But when people start to think about artificial intelligence, we're kind of poking the hornet's nest here. So once we think about machines that are not limited by thought, like machines that can think better than us, of course we're going to have people thinking, well, the world may end if we actually create AI. So this is how Hollywood portrays it, and it's very flashy, right? I mean, on the left, top left photo, we have Sophia, and that is a robot that made the headlines a few years ago for being a very close representation of a human that acted like an AI. Sophia was artificially intelligent, um, yet for reasons that we'll later discover, Sophia wasn't actually artificially intelligent. Sometimes you may get the more cute view of AI, like the dog in the middle. Oh, it's so adorable. It's a little robot thing, right? Um, and of course, we have the more doomsday scenarios on the right with HAL 9000 from 2001: A Space HAL 9000, right? Yeah, from 2001: A Space Odyssey, and the Terminator, the quintessential doomsday AI, coupled with Skynet. Uh, and because of media like that, it's no wonder that people are afraid of killer robots. However, I'll let you in on a potentially reassuring secret. AI is much more boring than killer robots. So, as summarized by Larry Tesler, AI is whatever hasn't been done yet. So, translation, if some task seems like only humans can do it, but ends up being solvable by a computer, it's suddenly no longer AI. This isn't a rule, it's just an observation of how we've kind of applied this term to technologies throughout the years. So consider this. At the beginning of the century, speech text recognition wasn't pervasive. So uh, on your smartphone, your keyboard likely supports a speech to text functionality where you tap the mic, and then you're able to talk, and it is voice dictation essentially. It converts the sound waves into individual tokens or units that get put into whatever app you're trying to speak type into. And once you consider that now it's really pervasive, you expect to see speech to text essentially everywhere you go. Not just on your phone or your keyboard, but also on the web too. Google Search also supports the ability to speak your query and get results. But 2 decades ago, it was nowhere as near pervasive. And later we'll talk about why that is the case. Why did only in the past 2 decades artificial intelligence become so pervasive? But this right here, this used to be called AI, speech to text recognition, because it was thought to be something that only humans could do. However, as our compute power grew, this is a spoiler, as our ability to compute grew, we were able to do things formerly thought impossible. And this effect right here, this moving the goalposts of what AI is called the AI effect. That is what Larry Tesler was describing with the quote on the screen. Um, and as we'll come to understand, AI is a deeply interdisciplinary field. So artificial intelligence is a very, very new field. Of course, philosophers like Aristotle have been thinking about uh, the nature of human thought for millennia at this point, centuries, millennia, sorry. Um, but well, up until recently, we haven't really had a way to formalize human thought. It was more conceptual and philosophical. How does the mind work? What is the nature of existence? It was very existential and high in the sky, but not very down to earth. So what happened? Well, reason happened. The mathematics, statistics, better better application of the scientific method happened. Um, so in contrast to how we've seen AI portrayed in popular media, in the world we live in, fiction is actually much stranger than reality. AI today is somewhat boring by comparison, but don't get me wrong. I love the field, and there are many things to be excited about in it, but um, many tend to believe in the killer robot fantasies of AI without realizing just how pervasive it is already. And as you see, AI really encompasses a lot of different methods to do something. But what is that something? Where do we begin? What is AI? Here is an observation I think best defines the field. AI is problem solving. It's simple to see how this field first came about um, as history has gone on. So first we try to think about how does the brain do things? Well, when we think about how the brain does things, do we just mean simple behaviors like how do we know to walk? Or do we mean more complex behaviors like how do we know how to drive? How do we coordinate our body so we can drive? Uh, questions like those are the ones we want to solve if we're going to build something like a self-driving car. Um, or doing things that were cognitively demanding. We want to try to solve those problems. And um, so AI, as I mentioned before, has roots in several different fields. It is very interdisciplinary. So we had philosophers thinking about the nature of human thought, and then in the 1800s we had the behaviorists who wanted to study the brain. So first came the introspectionists who wanted to just sort of subjectively describe their experiences and say, this is how I feel and this is why I did the thing that I did. But of course, that's very subjective and non-scientific. So then we had the behaviorists who tried to consider cognition as this kind of a black box. So it doesn't really matter how the brain works. The only things we care about are inputs and outputs. And if you're familiar with psychological conditioning, classical conditioning and opera conditioning, um, for example, Pavlov's dog experiment, where Pavlov was able to get a dog to salivate on command of a bell. That was one way that we started to explore human behavior. And that's connected to human cognition. But cognition didn't really become sort of a thing to be studied until um, after people realized the inherent limitations in only studying intelligence in terms of pure behavior. So we can't go further. We can't go further without discussing how this all began. We just wanted to understand the human brain. Um, Artificial intelligence didn't begin with people studying computer science or pure mathematics or statistics. It began with people studying the mind. And it wasn't until later that once we started to understand the mind and try to approximate it, we realized that the brain was much more complicated than we anticipated. And it's also a lot denser than we thought, meaning it's a lot heavier than we thought, meaning there's a lot more to the brain um, than we thought there was. There's a lot of baggage attached to it because humans, of course, are biological creatures. And you don't need most of the components in our body in order to make rational decisions. In fact, when I speak of the baggage of the human mind, when I speak of the baggage of the human mind, there are certain parts of us that are inherently not rational. We tend to react on emotion quite a bit, and that's we've evolved that way because it was core to our survival. It helped us build communities, but as we've seen in recent news with the rise of social media and fake news, sometimes that may not necessarily be the best at rational decision making. So first, we'll talk about a fundamental difference between methods in psychology and uh, yeah, psychology and modern computer science when we're trying to simulate, we're trying to understand the brain. So I like to characterize it as simulation versus approximation. So when we say we want to simulate the brain, we mean we want to emulate it. So for those of you who have experience emulating games, um, or for those of you who understand what a virtual machine is, we kind of just want to take an image of the brain, right, and run that on a virtual machine, and that is how we have artificial intelligence. Um, uh, there's some upsides to that, right? Well, for one, we actually, by doing this, we'd actually understand how the brain works. Um, and we'd understand how human cognition works, but the main downside is that uh, if we're going to simulate the brain, we need to do it accurately, which means we have to replicate all of the errors that it would make in decision making as well. So it's not necessarily an ideal means of solving tasks because, of course, our brains have certain cognitive biases built in, like confirmation bias, etc., that make decision making hard sometimes. So yes. And with approximation, on the other hand, we try to simulate, well, no, we don't simulate the brain with approximation. Um, we try to approximate the brain. So that means, for example, sorry, we're not necessarily trying to match exactly what the brain does. This is closer to the behaviorist approach where we have some input. Let's say maybe we want to know, or maybe we want to create something that can recognize images, right? Um, recognize different dog breeds, for example. We want a machine that can do that. Um, a human might have certain cognitive biases that we don't want to replicate in this machine. So with approximation, all we care about is, given some image of a dog, will produce the right breed that we want, right? So with approximation, it turns out it was a lot easier to approximate the brain than it is to simulate the brain. And as of right now, it's kind of the most dominant method used in artificial intelligence and machine learning. Of course, with simulation, cognitive neuroscientists are still actively trying to simulate the brain to understand how it works. But with most machine learning today, we try to approximate because we have this plethora of CS knowledge. We know how data structures work. We know how algorithms work. And we can mathematically prove that um, something is the best way to solve something. But with simulation, it's a lot more difficult to do that. So we'll consider searching as problem solving. So this is an example of one artificial intelligence uh, method. So let's say we want to find a certain node in a tree. So for those of you who have taken a data structures and algorithms class, how would you approach, say, trying to find the number 11? Okay, we'll start. So one thing to keep in mind when we're representing this. So this of course is a tree, right? Um, but with artificial intelligence methods, specifically search, we try to represent, we try to simplify what we're doing, our task essentially. So this tree right here could actually represent a maze, right? If we were to rearrange the nodes in the tree and then draw little walls around them, each of those nodes could indicate a yes, we're getting there. Depth or breadth first search. So uh, we're essentially trying to. This is a search problem, and with the search problem, we have an initial state. Say this is our initial state, and we'll say actually our initial state is starting at the node 1, right? And we have a successor function, which is how do we how do we transition states? How do we go from being in one spot to being in another spot? Um, so in this case, a transition function can just be going from 1 to 2, or just picking a node that is connected to any other given node. Um, so yes, we're trying essentially we're in this. If we want to find the node 11, what we could do, let's just pick a rule, like choose the node. If we were to look from the perspective of the 1 here, um, choose the node that is always on the left. And if you keep going and keep doing that, or go forward, or choose the node that's leftmost, right? Um, and if you run into a dead end, then keep track of the last fork, essentially. Keep track of the last child node in this tree that had, the last node, parent node in this tree that had a child. So with a simple rule like that, we're able to sort of dumb down a lot of problems into just simple tree traversal. Yes, and this is one way to do a breadth first search. Just applying a simple rule like imagine if you were in a maze, right? You know, and you applied this rule. Eventually, you would solve the maze. Breadth first search is complete, meaning it is guaranteed to find a solution in some amount of time. It may take a long time depending on how big your state space is, but um, it will find a solution, right? And artificial intelligence will use, well, breadth first search was, it still is a pretty important algorithm in artificial intelligence because it's very simple, right? And yeah, very simple to understand. So let's think of another example that might require some intelligence. So this one might require a lot more thought. So say we have a bunch of we have a lot of home information, and we want to try and predict how much a home will cost or how much a home will sell for based on some combination of its attributes. So these can include things like how many bathrooms there are in the house, how many bedrooms, how large it is in terms of square feet. So how would we do that? What would be a good first way of approaching this? So um, if anyone has any ideas, jump in. But so what we could do, right, since all of these are numerical values, and we kind of just want to find a line that can predict, except when we're trying to predict home price, well, we have multiple attributes to consider, right? It's not just that we're trying to predict home price based off of how many bathrooms there are, because there's a lot of, well, as we'll discuss with bias and variance, there was a lot of trade-off in doing that because if we were to draw a line purely based on the number of bathrooms, well, there's a lot of, let's say, well, variance. How far each data point will vary from the line we draw. But one thing that we'll observe is that once we consider more variables, we start to more accurately represent our data set. Um, so essentially, with this, what if we were to take a sum of weighted inputs, where each of those weighted inputs was, say, each of those weighted inputs would correspond to one of the columns in the table. So, for example, um, so the price is the thing we're trying to predict, right? And then bedrooms will say, maybe we'll multiply that by some constant A, and the number of bathrooms, multiply that by some constant B, square foot, etc., C, D, etc. So what if we were to do that and try to have some sort of means of adjusting those multipliers A, B, C, and D to predict the home price? Well, congratulations. This is multiple linear regression right here. We're trying to predict some singular output value, the price of the home, the sale price, right? And yes, could you predict using past sale? Yes, this is what we're doing. We're predicting using past sales, right? And this is beyond the scope of the talk, but we can use a process called gradient descent to actually iteratively adjust our model so that it gradually fits more and more of the data. Um, Gradient descent is a optimization technique that can be used to find some optimum maximum or minimum, and essentially, oh yes, uh-oh, okay. So let's consider this. In psychological research, there once upon a time was this thing called the perceptron, and the perceptron almost does what linear regression does. Say you have, yeah, say you have some node and you want to assign that a value and have this thing predict values based on how many are inputted. So this perceptron, instead of just taking the weighted sum of its inputs like simple linear regression does, it actually it applies some sort of function to it, which makes it different from just plain regression. We still train it using gradient descent, but we use what's called an activation function to determine the strength at which the node actually outputs a value. And the key part of this activation function is if it's non-linear, meaning um, if it isn't, let's say, yeah, if it's not linear, right? Meaning you can't decompose it into a series of additions and multiplications, then some very special things start to happen. And this is how neural networks started to come about. So you could try making the connection here that perceptrons are just one form of linear regression, except perceptrons can be sort of composed into neural networks that we'll talk about later. Um, but what makes linear regression so powerful as a method in artificial intelligence is, nowadays we don't really consider linear regression as artificial intelligence. It's definitely machine learning because we're trying to teach a machine how to model something in the world, whether that's a data set or behavior. So it uses simple rules about independent linear functions to produce some output. So as we saw in the home example, all we just summed and multiplied, some of the values in the table, and we gradually adjusted how much we multiplied and added those things to produce our predicted home price. So if you take an intro-level stats class, um, you may have learned that that linear regression only applies to a certain type of data, data that is IID, independent and identically distributed. So what does this mean? Independent data means each sample. So for example, each row in this house's data set is independent of the other, meaning one home price does not affect another home price. Of course, in reality, this is only a loose approximation. They're mostly independent. How much one home sells for is mostly dependent on what is inside of the house, not necessarily on how, not necessarily entirely on how the homes in the area sell. That's a significant factor, right? But most of the homes in the area tend to be very similar anyway. So for the most part, this data is independent. Home sale prices don't necessarily affect each other, or at least to a significant degree. And identically distributed means if we were to take some population of homes, for example, we tried to sample as best we could from all portions, right? We didn't just pick some local spot in the neighborhood and take all of our sample data from that. So because of the simple limitation of linear regression, because it really only works for IID data, and also since we're assuming by the way its variables interact, if you're familiar with y equals alpha x1 plus beta x2 plus c, you know that it's just a linear combination of vectors. And because of that, uh, we call this its inductive bias. We're assuming, right, that in order to predict something, we just need to find some linear combination of the variables in the function, right? Um, so an inductive bias is really an assumption we make in our data, and um, of course, there's a similarity to how perceptrons work and how multiple linear regression works. So um, they both involve variables of the things we want to predict, but let's consider why we can't use regression for everything. And as I mentioned earlier, it has to do with this inductive bias. The world is full of nonlinearities. So, for example, weather. We cannot easily predict weather using a few lines, for example. Right. Uh, and one thing to also consider is that these perceptrons, we can stick them together to build what are called neural networks. So imagine if you were to take perceptrons and kind of stick them together. So you line up your perceptrons in rows, and then you take those rows and you put them together, and you pipe the outputs of one row or layer into the next and the next and so on. And we get what's called an artificial neural network. And um, with this artificial neural network, it is the basis for what we call deep learning. So it is machine learning, except very, very deep and with lots and lots of variables. So here is, we're about to get to the fun stuff, don't worry. So here is, for those who aren't aware, what AI, ML, and DL are. And of course, um, if you only remember a few things, for those of you who are completely new to the field, this should be one of those things. So deep learning is a subset of machine learning, which is a subset of methods in artificial intelligence. So remember, more broadly, artificial intelligence is about trying to get machines to solve problems. But it just turns out that a lot of those problems are they're all computational in nature, but some are very numerical in nature. And with those, we can use something like machine learning to find a solution to those problems, whether that's predicting home prices, or even more advanced methods like deep learning, where we have artificial neural networks that can do even more crazy things and generalize even better than other machine learning methods. But of course, in practice, although there are other methods here, and this isn't an exhaustive list, although there are other methods that are arguably more functional in most of the cases, like you're probably not going to need a neural network most of the time. This is the hype that the field has kind of had for nearly a half decade at this point. It's kind of dying down, right? But the hype is still real. And the reason why the hype is so real with these neural networks is well, they're good at being universal function approximators. What does that mean? Oh, yeah. What does that mean to be a function approximator? Well, let us say we have some function like the true price, the function is the price of a home given, bathrooms, number of bedrooms, square footage. Um, but let us say that those variables were not linear. Let us say that by its very nature, home price was a nonlinear thing, and there are certain ways that the variables interact that we just can't quantify using linear regression. Deep learning lets us kind of avoid that by um, approximating functions um, that aren't necessarily linear. And if you recall from the perceptron from earlier, um, we apply a nonlinear activation so that we can approximate just about anything. So, okay, we know generally the history of artificial intelligence. We know a bit about some machine learning methods and kind of the intuition behind them. But now that we have an understanding about the core paradigms in AI, we can just talk. We can start talking about how some of the cool things are. So, in a way, I'll define new to mean anything that's really happened in the past decade or two, because although the field is although although the ideas behind the field have been around for a while, the last 2 decades have seen quite an explosion. We went from literally doing math, pencil and paper math to calculate how perceptrons behave on paper to, well, now we have machines. We have multi-billion-dollar cloud centers that can do these computations for us. So I'm going to show you the first real difference between AI now and AI in the 90s. So I'm going to explain to you this code snippet. So, yes. Okay. So for those of you who have experience with TensorFlow, TensorFlow is a machine learning framework built by Google. Originally, it was closed source, but Google open sourced it, and now it is a very popular one, along with PyTorch, which is probably more popular. But the TensorFlow website has a lot of documentation on, of course, how to use TensorFlow to do various AI type things. And one of the classic things you can do with AI now is it's almost kind of like a rite of passage. Image recognition. Image recognition has become so drop dead simple that you can do it on your own local machine, right? Before, you would need whole rooms to do computations, but now, your laptop can do simple image recognition. So with a few lines of code, we can train an AI to recognize images of numbers. Isn't that just blowing your mind right now? So I'll talk about, I'll briefly discuss. So of course, this isn't very implementation focused, but I'll briefly discuss how, or what is the function of each of these things. So right, so first we're importing TensorFlow. We're just kind of importing the library, and then we're creating our model. So TensorFlow has an API called Keras, which is what we use to build these models of image recognition so easily. So all we do, we just specify the shape of the image. We just specify this convolve operation, which is kind of like taking a magnifying glass and sort of scaling the image in a way. And then this max pooling, which does something similar, and we take an image, we kind of find the most salient parts of the image, and then we continually shrink it down. So yeah, this model.summary, if we were to run this code live, it would print out in our console. But eventually we get down here to where we add a classification layer. And since our task is predicting images of, predicting the number embedded in an image, so there's a data set called MNIST, where it's just a bunch of people's handwritten digits, 0 through 9. We're just predicting those. So because we have 10 digits to try to predict, we have this classification layer down here. And depending on the weight of the neurons in the final layer, the ones that activate the most are the ones that tell us which image, which number each image actually is. So we will take a brief detour to playground.tensorflow.org. So Google, of course, brilliant. The TensorFlow Playground allows us to play with neural networks. So let's transition. Okay, it's another one now. Okay, hi. This is the neural network playground. So I understand that a lot of the things I've been saying have been they've been kind of very theory focused, right? They're ideas, but here we get to see how neural networks actually do things. So if you look on the right, if you see our output, we're trying to create some sort of model that can clearly separate between these orange data points and these blue data points. We'll call these classes. So, and as I mentioned earlier, part of what makes a neural network so powerful is its ability to do things in a nonlinear way. So consider this. Would you be able to draw a line, a straight line to divide all these data points. So would you be able to separate all the orange, or even most of the orange, from most of the blue using a straight line? Of course, the answer by simple inspection, just imagine you just put your finger up to the screen and attempt to put a line there. No, you cannot. It is, you cannot put a line that separates those two data points. So what we can do is, using this neural network, we can train this neural network to predict some sort of boundary around the blue data points that separates the orange data points, right? And as we'll see up here, this epoch that is rapidly going up refers to how many times we are essentially applying our update rule. So if you recall from earlier with gradient descent, essentially we have some sort of rule that we want to apply. And this is how we gradually update our model so that we can accurately capture our data. So I'll pause this. And this learning rate, we'll play around with it. First we'll reset. Okay, so this learning rate controls the degree to which the update rule gets applied. So if we do, let's do a very small learning rate and see what happens. So when we say our model is learning, we really mean that our model is trying to approximate, or yeah, our model is approximating our data set. And you see with the learning rate of 0.0001, not much is going on. And that is because when we are trying to learn, we're trying to minimize the error in our decision boundary. Well, not much is happening because every time we apply the learning rate, it's so small that not much is going to be updated. And I think we did this already, but a learning rate of 0.001. You can see on the right side, we have this test loss and this training loss. And think of the loss as a function that tells us how inaccurate our model is, how inaccurate our model is from our data. So we want loss to go down because as loss goes down, accuracy tends to go up. And with a learning rate of 0.001, it takes some time, but the loss is going down surely. And the difference between this test loss and this training loss is that the training loss, this is where, well, I should have mentioned this earlier. With our data, we don't just have one set of data we're trying to optimize here. We have test data that we're actually using to evaluate our model. And an important part of machine learning, whether that's deep learning or traditional regression, is that we want our models to generalize to new data it hasn't seen before. So in order to do that, well, we separate our data set so that if the model that we learn does well in our training data, it'll probably do well in our test data. That helps it generalize. And if it doesn't, we know something's wrong, right? So as you can see, the test data is, it is distributed the same way as the training data, but it's different. And that's the important part here, because otherwise the model may overfit. So we'll experiment here a bit. We'll bump the learning rate up to 3, reset, see what happens. You'll notice what we're doing with this neural network is a lot more sporadic, and it's not actually learning any sort of decision boundary. So you'll see that the loss is rapidly fluctuating between, what is that, 0.3 and 0.67 maybe, which means our model is not generalizing the data very well at all. So it's important to keep in mind that our learning rate needs to be small enough so that we can still actually, so we don't bounce back and forth between wrong and even wronger, if that makes sense. We can even try playing with the learning rate, and oh, this is way worse. The activation function. And there are different functions we can use to kind of sort of adjust how each of these connections between our neurons inputs the output, or provides the output. Regularization, that is more of an advanced topic, so we'll try to, let's see, we'll try to explore these different features. So Yes, so each of these features is really some function on the data, right? And we apply some function. So for example, this is just taking the input data and, wait, yeah, we're operating on pairs here. So splits vertically, splits horizontally. This just squares the data. And, well, let's play around a bit. So we'll bump the learning rate back down to 0.01 because this tends to be a good learning rate. And, oh, okay, that seems to work. So it seems like I'm having a vertical line be a feature that we try to observe. Um, tends to converge quicker. Okay, what else can we do? I don't like that. Let's try doing this. Surely this might do something, right? Let's try this out. Oh, maybe it converges even quicker? Hmm. So I will leave it up to you to find the most optimal configuration to create a neural network to most quickly and accurately capture the training data. So that was classification. We can do something with regression, where each of the values before, yeah, each of the values before, is either, well, we could call this a 1 or 0 or true or false, right? Um, and classification is one machine learning technique. But with regression, we're trying to predict some sort of continuous value output. So that would be, for example, like predicting home price. So so if you can imagine, we'll just say that the x-axis represents bathroom size, and the y-axis, sorry, the x-axis represents square footage, and the right axis represents number of bathrooms. Of course, this is just a thought experiment, right? And the color indicates how how much the house actually sold for. That's what we're trying to predict. So let's play around a bit. And if we look at the data, we see that there's kind of this line in the center here. And we see that the data tends to be clustered on the top right and the bottom left. So we'll say low square footage means very low sale price, and high square footage means high sale price. But there tends to be this weird uncanny valley where the more bathrooms you have, wait, yeah, this is square footage, bathrooms, lower sale price. So more bathrooms, more square footage means a higher sale price, which intuitively makes sense here. Um, so we can try applying our existing rules now, and it seems to converge pretty well. Um, yeah, actually very well, very quickly. And as we'll see, it does a pretty good job of actually segmenting our data. Um, we can try experimenting with more hidden layers. So we'll just bump it up to 1. Reset, and go. So with more hidden layers, we can capture greater complexity in the data. And as you can see, it actually converged slightly quicker. We'll see, what was that? We'll rerun this experiment again. It took about, we'll say, 100 epochs to converge. Even though it's still going down, it's basically converged at around 0.05, 0.04. We'll try, see what happens when we just have one hidden layer. That's 2 neurons. How quickly does that actually converge? And, oh, interesting. For this data set, it seems like simpler is actually better, um, using less predictors, right? So this actually, if you watch carefully, it actually converged in less than 100 epochs. And of course, all of these are randomly initialized, but the rate of convergence is also determined on how we actually structure what features are important to our model. So I think that's enough experimentation in the interest of time with neural networks. So next, let's try moving on to transition. So next, we'll try moving on to something that you may have heard of. It is a very popular natural language generation model, GPT-3. Yes, so go to beta.openai.com. If you haven't heard of OpenAI, OpenAI is a company that does artificial intelligence research. One of their goals is creating artificial general intelligence, a form of AI that can generalize to essentially anything. Um, but with, let's see, OpenAI is very notable because of, well, its language models. OpenAI does other stuff, like with reinforcement learning, where we try to, uh, we'll talk about that later, where we try to optimize some reward. But what makes OpenAI's um, models nice is that they are very big. And as we observed earlier, large models tend to capture more complexity in the data. And the human language is very complex. There are very many rules, right? So if you scroll down a bit, you'll see demo. Yes. So what are we doing here? What are we exactly doing when we are generating text here? So OpenAI has an API that is, well, in very limited supply, we'll say, and it is able to take prompts and essentially predict outputs based on those prompts. So, this prompt is, we're releasing an API for accessing new AI models developed by OpenAI. Unlike most AI systems which are designed for one use case, the API today provides a general text-in, text-out interface, allowing users to try virtually in any language, English language task. And my mind, this is cool. This is really cool stuff. Um, Not even 5 years ago did we think we would have some way of generating text just by calling an API. And if you're not familiar with what an API is, an API is an application programming interface. It is a way of interfacing with, well, some piece of software. That can be some server, that can be some application. Um, but AI as a service is what OpenAI is trying to do here. So as we can see, with OpenAI's API, we are able to have this prompt, right? And this is what distinguishes machine learning from a lot of traditional software engineering. Um, in traditional software engineering, we already kind of know how the system works, so we essentially hard code that in what we're doing. But with AI, it doesn't know. Like if we tried to build a traditional software system to generate human text, we could only get so far. Like if you tried to write a script to generate human language, you would, unless you were very sophisticated with your means, you would produce you would produce language that would be easily determined not to be human. You could tell a bot wrote it essentially. But with these language models, although you can kind of do that if you try very carefully, uh, what language models do is they capture language. So if we consider our data set to be all of the words, not just the words, but a specific ordering of the sentences across multiple websites like Reddit, Twitter, I think, Wikipedia, we were able to come up with some algorithm, some model that based on the words in this prompt, we're able to predict the next words. So we didn't talk about LSTMs today, but LSTMs were one way that Google tried to, or sorry, Schmidt-Huber et al. Tried to do to predict one token or one word, one phoneme based on the previous ones. But as we see here, this is the prompt, in the gray here. And what makes this so crazy is that it is able to generate something that follows from this. So you can now request access in order to integrate the API into your product, develop an entirely new application, or help us explore the strengths and limits of this technology. The road to making AI safe and useful is long and challenging, but with the support of the developer community, we expect to get there much faster than working alone. So assuming that this demo isn't completely faked, we'll assume that this is in good faith, that this was actually generated by GPT-3, right? It's really convincing, is it not? It sounds very human. The road to making AI safe and useful is long and challenging. Not only was it able to accurately understand syntax, like putting comma at the end of a clause and then a putting a but after that and continuing the sentence. Um, it is able to understand to some extent the meaning of words, indirectly at least. So might be wondering, oh wait, let's try something else. Q&A. This is a better example of what's going on here. So GPT-3 is a general purpose language model. So you'll see this could just generate text, right? And this specific endpoint calls a function that literally just, well, we create the model here, and then based on some prompt, we say here generate 100 tokens, or wait, yes, a maximum of 100 tokens after that prompt. We're essentially completing it. But another thing we can do, because this is a general purpose language model, you know, as they kind of stated up there, is we can do question and answering, right? So we'll see their response is yes, yes. What year is the first fax sent? And the first fax was sent in 1843. It's plausible. It's coherent, right? And the language model doesn't necessarily know what fax is or what first really means. It just knows that in relation to the rest of the words, you know, given the presence of certain other words, this is a very plausible response. Uh, this is a very plausible response. So we'll keep moving. And of course, OpenAI does. You know, there are more parts to OpenAI's API that we didn't get to explore, but let's go forward. How are we able to have a language model produce new language based on some given prompt? Of course, the details of this are very much beyond the scope of this talk and would require a whole talk on their own. And actually, AIS is going to be working on a workshop to do specifically that. But we use what are called transformers. And transformers, no, not those sorts of transformers, essentially allow us to encode data and decode data in a way that preserves the relationships between words in a sentence. So with the encoder, what we're doing is think about it like this. Some language models will play a game of Mad Libs where given some paragraph of text, for example, we will mask out the words. Yeah, that's the actual term. We would mask out the words and try to have the model predict the words. And when we do that, we actually gain some information, right? We of course we choose randomly, right? Like filling in the man had a blue, right? There are many different words you could put there. You could if you aren't really considering the sentence, you could say the man had a very blue chair. The man had a very blue wall, right? And those words may be technically correct, but they aren't very likely. And when it comes to language models like these, we want to consider phrases that are most likely. And when we do that, well, it sounds plausible, right? So what would audience, how would you complete the sentence, the man had a blue? So me personally, I could say the man had a blue tie. That seems plausible. The man had a blue suit. The man had a blue. Yeah. That's as far as my imagination goes. So transformers, they essentially do that. You can use transformers to do that masking activity, and you gradually understand the structure of language. So given some set of input words, we use a mechanism called attention to find out which words are most important in predicting the next word. And we sort of consider sentences instead of these long sequences of words, right? Like the quick brown fox jumped over the fence, right? Um, I think the sentence, yeah. The quick brown fox jumped over the fence. Instead of considering each of those words as the and then quick and then brown and then fox, and this is what makes attention so great. This is what makes transformers so great. We don't need to rely necessarily on only the next word or the preceding or the succeeding word. Google's bidirectional LSTMs tried to do this. It tried to use the word behind the current word and the word in front of the current word to predict what should go there, right? First it would do a forward pass, like try to predict the words, saying like the quick brown fox jumped over the fence, and then going backwards, it would modify it so that you have a more accurate sense. But attention, we don't need order at all. Well, we kind of do, because otherwise, I'll say this. We consider words as sets, but sets with positional encodings, and our workshop will talk about this. So once we consider words as sets, we're able to predict based on some given set of words and their relative positions in the sentence. We're able to predict what happens afterwards. And I'm grossly oversimplifying this, so please come to our talk when that is ready. But unfortunately for us, OpenAI isn't that open with their language models. It is closed source, and Microsoft maintains exclusive rights to just say license it. But Hugging Face is a company that it makes open source language models, and they're very important. They are very well known in the ML community. So if you want to experiment with language models on your own, then this is a good place to start. And it does something very similar to like TensorFlow or Keras, where it's just a simple Python import. And this is amazing because we can just import some model, right? And these models are just um, they're basically just glorified sets of numbers and labels. Labels for how the model is structured. So we're able to just import the model and apply the model. As simple as that, just as we saw with OpenAI samples. So if you're interested more in natural language processing, check out the Hugging Face website, which is unfortunately covered by my camera. Links will be in the description after this talk. So yes, next demo. We'll try making some music using AI. Let us switch. Okay. If you cannot hear this, please let me know as soon as you can. So we've classified images. Well, we can classify images. We can predict language. But well, they say music is a language of sorts, right? So how do we do that? Um, this is a demo. So I displayed some melody, right? And our goal is to produce some counter melody or some melody on top of that, predict some sequence of notes with given timings that harmonize, that make for those of you that music theory experience will say, that make the notes sound more pleasant together. So this Google AI experiment, well, so what happens? We're using machine learning here to emulate Bach. So yes, as it says here, this machine learning model was trained to analyze 306 Bach compositions and uh, predict notes that would match how Bach would play. Is it training? I can't tell. I don't believe it's supposed to take this long. Let's see. Are we gonna? Okay, and here we go. So oh, I'm so sorry. Can't hear it. Very quiet. Okay. So is the sound better now? Oh, okay. It's okay now. Okay. So we'll listen one more time. Okay. I'm going to assume that the sound issue has been resolved. So for those of you with music theory experience, well, this is plausible, right? I mean, I can kind of I have experience reading sheet music, and there's a very interesting way to represent this, where the lengths were the length of the line indicates the length of the note, and the relative positions on the staff, they still make sense, right? But we'll listen one more time. Yes. How do we do that? Well, I'll let you. Uh, the link is wait, yes, it goes up here. So how exactly are we generating melodies? So do we have time for that actually? We might need to let's see. Yeah, actually, we do not have time for that, so we will skip that. But if you're interested in how to do these sorts of activities with generating sequences, um, look up the term oh, recurrent neural network. That'll get you started. So with the current neural networks, um, they're different from traditional neural networks, except these have state attached to them. So neural networks, really, same thing with linear regression. They're just a function that we apply to some input, right? And we're gradually updating the function. But with recurrent neural networks, we update the function in a different way. There's a part of the function that has state, meaning it given some um, given some input after some other input. Um, oh, sorry. Given some input, if we apply the function twice, we're not guaranteed to get the same output, right? Because of the state. And the state interacts in a way that helps the model learn and generalize better. So if you're interested, check out what recurrent neural networks are and more details. We are going to have a workshop later this semester that talks more in depth about using AI to generate these sorts of things with art. For our final demo, we'll try making this very brief. So if you're not familiar with what reinforcement learning is, as I alluded to earlier, we're trying to optimize for some sort of reward. So let's say you're playing chess. You get a reward every time you win, right? As a human, like, yes, I won. I checkmate. But with machines, we might need to be a little bit more explicit than that. So with with reinforcement learning, we we essentially tell it what is right and wrong. Well, an exception. We tell it what is righter and wronger through this reward function. And through this reward function, we were able to sort of guide the agent, this thing taking actions in a world, to make better decisions or decisions that get it to do what we want it to do. So you could apply this mental model to doing things like playing Minecraft. Maybe your goal is to uh, get as many diamonds as possible in a 10-minute period, right? When we're training our model, you could, let's say, give it a reward for chopping down trees, right? Because you need trees to make planks, to make sticks, to make pickaxes, to mine, and so on and so forth. We can also apply this more simply with AlphaGo and more advanced reinforcement learning methods. They tend to specify, well, we don't specify the reward function for them. AlphaGo, what makes it so powerful is it was able to determine by itself how its reward should be based on the given state of the game. So if you're not familiar with the video game Go, board game Go, um, it is a board game where you there are two players, yeah, two players and two opposing sides. It's supposed to simulate war, so I've heard, um, but there are certain sets of rules. Well, because of its rules, it makes the game uh, significantly, orders of magnitude more difficult to solve than chess. Because with chess, with a powerful enough computer, you can calculate every single, you can use, what is it, breadth first search, or I think you can use some form of search to uh, find, given the current board state, what is the best move to make next? What is the move least likely to checkmate me as soon as possible? Just a very roundabout way of saying we can use search, but AlphaGo, it used a combination of search and reinforcement learning because we cannot use search for Go because there are more possible board configurations to Go than there are atoms in the universe. So with that, let us talk about this demo. Try to be very quick. Oh, okay. We will switch to next demo. So this is a demo from Stanford, and it's more in depth. And of course, all these links will be in the description after the talk. But so yes, there was a paper by some others and David Silver. It was from DeepMind and playing Atari with deep reinforcement learning. This was actually a very very pivotal paper because it introduced the idea of deep reinforcement learning. So DeepMind tried to train a reinforcement learning agent to play Atari games. So everything from Breakout to Space Invaders. But what made it so powerful and effective was this deep Q learning. And there's a lot of math involved with this, right? If you're familiar with the Markov decision process, um, they use a Markov decision process to model the world in the world state, and The powerful part here is they were just able to pass in entire images, right? Whole images of games, right? And they sort of pump them into this neural network, and it was able to predict the best state given some set of frames for the game, right? So uh, it is a paper you should read if you want to get more in depth, but I wouldn't start with it because it requires that you know some things about probability statistics. But for this, this demo from Stanford really shows us well. But I think I'll let this image explain it for itself. So we will. This model has actually been training in the background throughout this talk. So right now we see that it is its objective is trying to get the green or just yeah, its objective is trying to get the dots, right? And as you can see, it has a range of view, and that range of view is used to, well, it's piped into the neural network to tell it where to go next, right? Um, and as you can see, yes, the right is the average reward over time. So this algorithm or this model is converging, right? It's slowly going up, right? And eventually its reward will reach some sort of maximum as it becomes more intelligent, right? But we'll see what this thing looks like without the training. So from the beginning, it's taking random actions, and well, let's go normal speed. It's taking random actions, right? And it doesn't know what it's doing. And as you can see here, its reward is well, it's slowly going down, right? Because its goal is trying to get the dots, right? And it's trying to use these little rays, these little lines to give it input to make the decisions. So um, in the interest of time, we'll skip over some of the finer details, but essentially, it's trying to optimize some reward function based on its current position and how it's looking to um, explore the area and using what it knows, using its value function that using a neural network that returns some sort of value that tells it how good its current state is. Um, it explores and tries to get as many dots as possible. So, without further ado, um, you can see what happens once the model converges. It becomes more intelligent. Of course, it's not perfect. It still has a lot to learn. As you can see, it's kind of struggling in the corner. But we will, in the interest of time, march forward. Yes. So one final note on reinforcement learning. We may or may not have a talk on this later this semester, but as I mentioned earlier, we try to optimize some reward functions. So each of so yeah, the dot or the agent moving around, right, trying to get those other dots. Well, that was the agent. That was the thing taking actions, right, as you see on the right-hand side. That is an agent that takes actions in the environment, and the environment was the game in that case. And every time it took an action in the environment, we got some sort of reward and state. So the state can be we can represent the state in a variety of ways. We can say, here's an image of what the environment currently looks like. We could say the state is how near the current item is for you. It could be a vector, a scalar, it could be just about anything, right? Uh, but we're trying to optimize this reward here. So there's this interaction between the agent and the environment, and um, reinforcement learning tends to work out better when we have a clearly defined objective function. So with image classification, it is very hard to say, this is what a dog looks like, this is what a cat looks like. All we know is that cats tend to look like this, and dogs tend to look like this. We can't just say, because if we could just write a function that just says, here is cat, here is dog, we wouldn't need machine learning in the first place. But with reinforcement learning, uh, it tends to work because we know what the goal we want is. So, for example, maybe getting the most, collecting the most dots in some period of time. Um, yeah, because we know that goal, we can better optimize for it and say, okay, if you see, right, we'll give you a better reward if you can see a dot, right? And gradually over time, the agent learns that as that reward goes up, right? So as it sees more dots and approaches them, like the closer you get to the dot, the higher your reward will be. We can gradually shape behavior that way. So I think I have spoken enough about uh, reinforcement learning. So that is currently what is new with machine learning and AI. But what happens after this? We have language models now. We can predict and classify images with ease. We're starting to be able to generate art. But let's take a glimpse of the near future. So AI is appearing in many domains. It's starting to appear in many domains. So um, it used to be in the domain of psychology and computer science and statistics, specifically machine learning. But now we're starting to realize we can apply intelligence to solve many problems, like with agriculture to make crops more efficient, or business to find ways to maximize revenue to shareholders. Um, and this pattern here is very, very clear. AI in X is the next big frontier. So um, even in economics, right? Traditionally it's been pretty static, but with AI in economics, um, we can, for example, optimize tax policies so that people are satisfied with the rate of taxation that they have, but the government gets as much money as possible to fund social services. And AI, specifically machine learning and physics, can be used to even discover new particles, right? So because machine learning is good at detecting patterns in data that humans can't, that is what makes it well suited for physics. And robotics, of course, very prime application, using machine learning and reinforcement learning, especially to train robots to, perform non-routine tasks, right? And of course, AI in art. Due to advances in machine perception, we also have come up with advances in generation of things. So we went with some few notes. So if you want to understand how modern AI is driven, know these three things. Modern AI is driven primarily through compute, not algorithms. Meaning, often it's not really how smart your algorithm is. It's a lot of times how big your computers are. And we're potentially running into some issues here with um, how accessible research is to people with who don't have access to supermassive, supercomputers. Um, but this should be clear from the way language models are growing. So um, the bigger language models get, as we discussed earlier, the more accurate, or the more complex, but the more accurate they tend to be. But that requires a lot more energy. Um, so the field currently relies on statistics a lot, which is good for all the domains we try to do. It's good for optimization, especially. Um, but for more discrete things, it tends to we need some additional methods, and some researchers, like those at the MIT IBM Watson AI Lab, are working on neural symbolic methods that combine one thing we didn't talk about, um, symbolic ways of symbolic methods of intelligence with the traditional neural networks we know, and produce AI that doesn't require as much data to train. All right. And the final point, AI developments are often inspired by insights from other fields. I mean, AI is inherently interdisciplinary, and it started off as um, yeah, it started off as this exploration of the mind and psychology. So if you're still here, it means you must be reasonably passionate about the field, and I don't blame you. This stuff is interesting. So you may know that you uh, should have a strong math and computer science foundation to um, really get behind the nitty gritty of machine learning, but you really only need to understand specific subfields like probability and statistics, data structures and algorithms, some calculus and linear algebra. And that is if you really want to understand what's going on. If you just want to apply machine learning to your project, um, you don't necessarily need that much mathematical experience. With probability and statistics, we're able to understand how uncertainty affects things. With data structures and algorithms, we're able to create efficient um, data containers to manipulate models, and optimization allows us to optimize models. And linear algebra is kind of the way we conceptualize how different variables interact with each other. So if you want to start small, start off with Google's machine learning crash course. It is good at understanding the conceptual foundations behind machine learning, which is a big part of AI. And of course, there's Andrew Ng's course on Coursera, and there's also courses taught by people here at UTD. So, there's an Intro to ML class, there's an Artificial Intelligence class, one on Natural Language Processing. Consider taking those because ultimately, AI is a big field. So you need to sort of pick one thing and go very heavily in that direction before you try branching out, right? But I think this concludes our talk. Thank you very much for listening. Next week, AIS will be having a more in-depth hands-on event showing you how to implement sentiment analysis for movie reviews using basic natural language processing techniques. We highly encourage you to come. So best wishes on your AI journey. If you have any questions, feel free to drop them in our Discord at aisutd.org/discord or email us at contact@aisutd.org. Thank you.